Hi there, let's deal with our last section or topic before our quiz, and that is looking at one way we test water for contaminants. And that is through the understanding of acids, bases, pH, etc. We use something called the pH scale, which actually stands for the percentage of hydrogen. And again, pH stands for the percentage of hydrogen in a solution. The more the hydrogen ion, the lower the pH. So the pH scale usually starts in the middle at pH 7. And when it comes to water quality, that's pH 7 is what we're looking for. Healthy, good water is neutral and therefore pH 7. But if more and more hydrogen ion ends up in the water, then the pH goes lower and lower and lower. And it becomes harder and harder to live in. Most living organisms have a hard time surviving in anything that is lower than pH 4 when it comes to water. Now, when we go above 7, we say that it becomes more and more basic or alkaline to a point of pH 14. So how does pH work? Well, acids are considered solutions with a pH of 0 to 7, not including 7, so below 7. The lower the pH, the stronger the acid, and bases have a pH above 7 all the way up to 14. The higher the pH value, the stronger the base. An acid is a substance that breaks into hydrogen ions in aqueous. Aqueous means in a solution dissolved in water. And a base or alkaline breaks up into something called hydroxide ions. What happens to the pH of substance is 7. It's considered neutral. What is the pH range of acid on a pH scale? 0 to 7. What's pH base? There we go. Now, acids have certain characteristics. They generally taste sour. Mind you, I don't recommend you taste something if you don't know what it is. And they turn blue litmus paper red. And think of lemon juice. How about bases? What are their characteristics? They taste bitter, like a stomach remedy called milk of magnesia. They feel slippery, like soap. And they turn red litmus paper a blue color. So what about the pH of Calgary's tap water or the pH of swimming pool? That must be checked periodically, and why? Is it important for lakes and rivers to maintain a certain pH? Well, let's look at that. Here's the pH scale again, and here are some common substances and what their pH is. Battery acid is almost pH 0. Lemon juice is about a pH 2. Tomato juice, about a 3.5. Coffee, somewhere around 5. Milk, 6.6. Blood is a little higher, 7.4. Baking soda is a little higher, and household cleaners. And so there's a trend here you should be aware of. Lots of or most food substances are slightly acidic, and most cleaning products are alkaline or a basic. Here's pH paper. It's made from plant extract, and we dip the paper that you see here into the solution, and then we match its color to a color chart. And usually darker reds indicate higher or stronger acids, and blues indicate bases. Acid rain used to be a huge problem in the United States, and due to newer technologies and a concerted effort by governments and people, acid rain is not so bad a problem anymore. Let's look at 1992. In the United States, lots of the concentrations of precipitation were often into the red zone, which is almost close to 4. And there's heavy population over here on the eastern seaboard, which would help cause that to happen. Let's look at how living things do with pH. Again, pH 7 is best, but at about pH 4, all fish would die. 4.2, you wouldn't find any more fish. Okay, most clean rain or healthy rain is a little slightly acidic. A healthy lake is about 6.5. This is an alkaline lake I wanted to show you. This isn't human related. Acid rain formation is human caused, and so what happens is you get pollution from factories and exhausts from trucks and cars, and they cause sulfur dioxides and nitrogen oxides to go into the air, and then when it rains they come down as sulfuric acid and nitric acid, which causes the water and the soil for that matter to be acidic. We test pools. Oh, back to alkaline lakes. This is limestone, and when it rains, the lime dissolves into the lake, and that can cause the lake to be highly alkaline, which could be deadly. So this lake, for example, that you see here doesn't have a lot of living things in it. No plants, barely. You can see some of the plants, but they're pretty dead right there. And so it's because the pH of this lake is somewhere around 9 or so, so too alkaline for most living things. We test pool water like this guy's doing right now, and the reason we do that is pool water has to be disinfected from bacteria, algae, etc. And the way we disinfect it is we usually use chlorine or bromine or something like that. And if it's too acidic, it can irritate your eyes, but more importantly, the chlorine doesn't work very well, or the bromine that you use to disinfect the pool. So anything really low will cause bacteria or some bacteria to thrive because the chlorine doesn't work anymore. This is liming trucks. Here's what happens sometimes in Australia. If the soil, due to pollution, gets too acidic, then they'll use a lime to neutralize the acid. So it's a weak base, the lime, and it's shown here. The trucks use limestone, and basically it neutralizes the pH of the soil, so it's back to pH 7 instead of something really bad. We sometimes use indicators like the pH paper, but this time in liquid form. So bromothymol blue is one type. It helps us know whether the water is bad or not. So if the water is blue in color, that means it's high in pH, above 7.6, and if it's yellow, that means it's acidic. And so we want it somewhere in between. Same with phenolphthalein. It helps us know whether it's too alkaline, because if the pH of the solution is above 8, it'll turn fuchsia color. Just a quick did you know, farmers and gardeners used to taste their soil to determine its pH. If it had a sweet taste or smell, it was kind of basic or alkaline, and if it was sour, that meant it was too acidic. And here's how lots of living things do when it comes to pH. So as we talked about, healthy water likes to be a pH around 7, even 6.5. This graph shows you at what pH range these organisms will survive in. So trout will not survive below pH 5. Bass, which is a type of fish, 5.5. Frogs are a little hardier. They'll make it up to pH 4, anything below pH 4, and they're pretty much dead. Salamanders, again, pretty hardy. They'll make it to about pH 5. Mayfly, which is a kind of insect larvae, snails, crayfish, they're less hardy. So again, this really shows you how important it is to keep lakes and rivers and streams void or away from the problem of acidity or acid rain. Let's look at this quick video clip about how indicators work. Hi there. Welcome to my video demo on acids, bases, and indicators. Right now we've got a little bit of sodium hydroxide, so not much hydrogen ions, not much hydrogen ions. Watch what happens when we put a little indicator in there. Ooh, we get a nice dark purpley color. Watch that settle a little. Let's give it a little stir just for good luck. Let's mix that up. Beautiful. Beautiful. What that indicates is it's highly basic. We've got universal indicator solution, which changes color depending on whether it's highly basic or highly acidic. Now I'm going to drop an Alka-Seltzer tablet in there. It's going to sink to the bottom. Alka-Seltzer tablets produce carbon dioxide, and so the carbon dioxide is starting to bubble up in the solution. Eventually, it's going to rise to the top, but watch what happens with the color change that's going to go on here. Nice, we get a nice color change happening as it comes to the top. Look at the nice, beautiful green going on. Move her back a bit. Splendid. Now a little yellow. Oh, green. Look at that. My final step. Here's the CO2 tablet coming to the top. And step 3. Let's change it one more time. I just added some vinegar, which is an acid. So now we're going to change this column back down to highly acidic, which is red. Colors of the rainbow, folks, thanks to indicators.